Hi, I'm Dr. J, and this is a video about hypothesis tests. As usual, there's a PDF down below in case you want to print these out, and there'll be a link up here to the playlist all about statistical inference, including Bayesian and non-Bayesian approaches. In this video today, we'll talk about the general construction of hypothesis tests, and we'll use a binomial example throughout. A hypothesis test has two hypotheses. One is called the null hypothesis, and the other is called the alternative hypothesis. Now, I've already had a whole video on hypotheses and specifically the null and alternative, so that'll be linked up here somewhere. But basically, these are models and statements about parameters in those models. And the goal of a hypothesis test is to make a decision. And the decision is either going to be to reject the null hypothesis or to fail to reject the null hypothesis. And we'll talk toward the end about what that actually means. For now, we're going to think about a binomial model, and we're going to introduce some of the hypotheses that you might be thinking about for this particular model. So the binomial model, which we've talked about quite a bit before, is the model for coin flipping with some probability theta. That theta is typically the parameter that's unknown, and hypotheses will typically be about that parameter theta. In particular, a common null hypothesis says that theta is equal to some particular value. For example, if you're thinking about coin flipping, then maybe your null hypothesis value will be that the probability is 0.5. If you're thinking about a die, and rolling a die, maybe it's six-sided, then the probability might be 1/6 for landing on a particular side. So that'd be the null hypothesis. The alternative then, in this case, is going to be that that's not true. That is, that there's a probability, but it's something other than the one that you're specifying. But now we can construct, this is called a two-sided hypothesis, but we can also construct one-sided hypotheses, and these basically say that there's a directionality in these two hypotheses. So one is that we could say that the null hypothesis says that the probability of success is less than some particular value, theta naught, and the alternative being the opposite, saying that it's greater than. Or we could go the other direction and say that the null is that it's greater than, and the alternative is that it's less than. And now, always in the null, we're going to have the equality piece. And in fact, sometimes it's going to be more convenient to think about this as the null always just being the equality. Okay? And other times it's going to be useful to think about partitioning the space of the possible values for theta into two different sets. And so we might want to be thinking about less than or equal to versus greater than. All right, so we might go back and forth between those two. Mathematically, this is how we actually are going to derive what we're looking at. So we're going to have the equality sign on the null hypothesis. All right, so let's consider a particular example. So suppose that you have the standard null hypothesis here that the probability of success is 0.5. So you're thinking of perhaps coin flipping, and the alternative is that it's not 0.5. And now you've collected some data, and out of the 13 attempts, you have 6 successes. And the question now is you have to make that decision, and the decision is, should you reject this null hypothesis? And if you think about this a little bit, you think, well, if I saw 6 successes, that's pretty close to what I expected to see, right? If you calculate the expectation, that's n times theta, that's 6.5 in this example. And so that 6 that you observed is very close to that expected value, and therefore it doesn't seem like you should reject. So probably not. But what if, instead of observing 6 successes, you saw 2? Now, if you saw 2, that's getting quite a bit farther away from what you would expect. And so one idea that you might have is to just calculate, well, what's the probability that we observe 2? And so we can do that, and we can find that that probability is pretty small, 0.01. So only 1 in 100 times, approximately, would we see only 2 successes if we had truly a binomial model with 13 attempts and probability of success 0.5. And that might lead us to suggest that, yes, we should use this as a criteria to reject. This isn't going to quite work, and the reason it's not going to quite work is illustrated here when we increase the sample size. So now we're up to 13,000 attempts, and in those 13,000 attempts we see 6,500 successes. Now you say to yourself, should I reject the null hypothesis? And the answer probably pretty quickly should be no, because 6,500 is exactly the expected value, right? That's that n times theta naught. All right, but if I were to calculate the probability of observing exactly 6,500, that's pretty small. In fact, even smaller than the previous slide, right? And that just comes about because there's so many possibilities when you're doing 13,000 attempts that any one of those individual possibilities has a relatively small probability. So we're not going to quite do these approaches, but what we're going to do instead is we're going to calculate something called a p-value. Now I had a whole video just on p-values. Hopefully they'll be linked up here. And the p-value is, here's a definition I'm giving that's slightly different than the definition I gave in that previous video. We're going to calculate the p-value is the probability of observing a test statistic as or more extreme than observed if the null hypothesis is true. And the words in red here are those that I've added or modified in the definition I've given before. Because we're going to do a hypothesis test, we now sometimes refer to the statistic as a test statistic. And I've changed the word model into null hypothesis. But really, we're still thinking about a model. All right, in this p-value, there's one key step. I mean, lots of key steps, but one in particular that oftentimes causes confusion. And that's this as or more extreme region. And the key is when you write out the hypothesis test, that as or more extreme region is going to be determined by the alternative hypothesis. So for instance, if our alternative says that the parameter is less than a particular value, then we would expect our data to be less than a particular value. So in this case, we're going to use our data, our observed data, as the test statistic. And our as or more extreme region is just going to be those values that are smaller than what we have, or equal to what we observed. Because if theta were smaller, that's what we would expect to see in that alternative hypothesis. We can go the other direction and we can say, well, what if our theta was actually bigger, right, than the proposed value? Well, then we're going to look at values of this random binomial that are larger than what we observed. So that's going to be y greater than or equal to little y. If we think about the as or more extreme regions, then we're in the situation where we want to be perhaps farther away from the expected value. So if theta naught is the null value, then n theta naught is the expected value. And the question is, what is more extreme than what we observed compared to that expected value? And this is the region right here, where now there's really two parts. We can either be to the right or to the left. And so to do it concisely, we use absolute value signs. So we calculate this quantity, y minus the expected value, for both the observed on the right and for the random variable on the left that we're going to use to calculate this p-value. And when that random value is farther away from the mean than what we observed was from the mean, then that absolute value on the left side is going to be bigger than the absolute value on the right side. Now, before in the previous video on p-values, we depicted this via the probability mass function for a binomial. And so we can do that again here. So now we have the less than on the far left. So that's just a few points down there. They're really hard to see in that magenta color. We have the greater than on the far right. So there's lots of mass there. And we have the not equal to in the center, where as we did before on the previous video, we can see that the area in that not equal to is symmetric on the two sides. And so later we're going to use that to calculate the probability. And so basically the p-values are just these areas under these curves, right? Or that is calculating these probability mass function values and adding them up. So to demonstrate that, if we have our alternative that says that the parameter is less than 0.5, we're calculating the probability of the random y being less than or equal to the observed y. That's just evaluating the cumulative distribution function for a binomial. In R, we'll use the p-binom function to do that calculation. And in this example, we see a probability of 0.011. So that would be our p-value. If we had the alternative hypothesis where we had greater than, now we have to calculate the probability that y, the random binomial, is greater than or equal to the one we observed, little y. We showed last time how to calculate this, but we'll just plug it in. In this case, it's a very large value, 0.998 or so. And then we can do the two-sided hypothesis. And in this case, we're just going to multiply that first p-value by 2, because if you go back and look at the slide, you can see that those two areas are equal, and we find a p-value of 0.022. Now, typically we're not going to do this by hand, but instead we're going to do it using R's built-in functions. But I just wanted to show you that the results are going to match. So here's R's functions. The function is binom.test. You plug in y, you plug in n, you say what the alternative is, and what the value for theta naught is. And there you go. So now we're just looking at the p-value, and we can see that throughout, as long as we get that alternative correct, we see that we get exactly the results that we had on the previous slide. Okay, so now we've got this R calculation. We've calculated the p-value for whatever particular hypothesis test we want to do. And now we have to remember that the whole goal was to make a decision. The goal is to make a decision to either reject the null or fail to reject the null. And so typically what's done is to assume beforehand a significance level that I'm referring to as A. This significance level is set up such that if the p-value is smaller than that significance level A, then you say we reject the null. And if it's not smaller, you say we fail to reject the null. So now we have a way to make a decision. Typical values for A are things like 0.05, 0.01, 0.001, something like that. When we make this decision, there's two possibilities, but overall, depending on what's true and what decisions we make, there's 4 total possibilities of what could happen. That is, on the top, along the columns, we have that either the null hypothesis could be true or that it's not. Down the rows, we have either that you reject the null or you fail to reject the null. And now, depending on which combination we have selected, right, either we're going to make an error or we're going to be correct. So, for instance, if the null is not true and we reject it, then we're correct. If the null is true and we fail to reject it, then we are again correct. The other 2 situations are both errors. And it turns out that if the null is true and we reject it, we call that a type 1 error. If the null is not true, but we fail to reject it, that's called a type 2 error. And I bring this up because I want to relate it to that significance level on the previous slide. The significance level is precisely the probability of rejecting the null when the null is not true. So by setting that, you set this probability. The other term to talk about is something called power. So power is the probability of rejecting a null when that null is not true. So oftentimes in talking about these hypothesis tests, we talk about the type 1 error, which is the significance level, and we talk about power, which is this probability of rejecting if the null is not true. All right, so great. So we can make a decision, but what does that decision really mean? I want to remind you that the null hypothesis is really a model. This model is, in the example we've been looking at, is a binomial model with a particular value for the probability of success that's equal to theta naught. And if we reject that null, then we are saying our data are incompatible with this model. As a reminder, a binomial model you can think of as having underlying this binomial model a set of Bernoulli random variables. These Bernoulli random variables are assumed to be independent and have a common probability of success theta. So when we reject the null, what are we really saying? We're saying that our data are incompatible with this model, which says that perhaps the xi, the underlying Bernoulli random variables, are not independent. Perhaps there isn't a common probability of success for all of these underlying Bernoulli random variables. Or perhaps, in fact, the probability of success is not equal to the particular null hypothesized value of theta naught. Or perhaps we just got unlucky. Right? That unlucky part is really what that significance level is meant to outline. So if you reject, it really could be any of these things that are the problem. And so the emphasis here I want to make is that you need to do your due diligence to make sure that these aren't the cause of that rejection. Okay? Or maybe eliminate some of them so that some of the other ones could be. Now, if you go the other way and you fail to reject the null hypothesis, what does that mean? Really what that means is that we have insufficient evidence to say that the data are incompatible with this model. Right? That's very wordy. I mean, why can't we just say we accept the null? And the reason we can't just say something like that and we have to be wordy like this is because that's really true. There's just insufficient evidence to say that the data are incompatible with this null model. Right? One of the easiest ways to fail to reject is just to not gather much data. Right? If you don't gather any data at all, then you can't reject it. Right? And that doesn't mean the model is true. It just means we don't have enough evidence to say that it's not true. All right, let's finish up here with a die tossing example. So we're playing a game of Dragonwood, right up here on the shelf. And in that game of Dragonwood, you're playing with a friend, or at least they were a friend. That friend rolls a 4 in their first 6 attempts, they roll a 4 3 times. And if you're not familiar with Dragonwood die, they're 6-sided dice. So here's a Dragonwood die. And they're numbered only from 1 to 4. And that is, there's 2 2s and 2 3s. So 4 is actually the largest number on the die. And so your friend rolling 3 out of 6, this seems suspicious that they rolled the maximum value in the die 3 out of 6 times. And you want to say, well, what kind of evidence statistically is there that something might be going on? And in particular, you might have a particular alternative in mind. That is, you think your friend has done something perhaps to increase their chances of getting a 4. And so we might set this up in this way. We might say, let y be the number of times you rolled a 4. And we're going to assume that there's a binomial random variable with 6 attempts and a probability of success theta. Our null hypothesis might be that the theta is equal to 1/6 because it's a 6-sided die. And the alternative might be that it's greater than 1/6 because maybe you think they're cheating in their favor. And now suppose you observed 3 successes, like we said. Then we can just plug this into the binom.test function in R with 3 successes out of 6 attempts, the probability being 1/6, and our alternative being greater. And we find here that the probability is 0.06. So now you have to make a decision. Perhaps you decided on a significance level ahead of time of 0.05, and you would say you failed to reject the null hypothesis, right? And so far, there's not enough evidence to say that your friend is cheating. All right, to wrap up, we talked about hypothesis tests. In particular, we talked about a null and alternative and making a decision, typically based on a p-value. Either we reject the null, which says your data are incompatible with the model, or you fail to reject, in which case you have insufficient evidence to say that they are incompatible. The data are incompatible with the model. Now, I want to emphasize here that just because you get a rejection doesn't mean that's the end of the story. You need to do your due diligence to make sure that there aren't other reasons for why you are rejecting. Things like independence or other model assumptions. The next video we'll talk about the same structure, but talking about in the context of a normal model rather than binomial. Hope to catch you there.